Hey guys, we're going to start off by talking about the number systems. So you should be familiar with them. You might have heard natural numbers, whole numbers, which you don't see here, integers, rational and real numbers, probably irrational in there too. The reason we're not including whole numbers is because there's debate on those. Depends on who you talk to as whether or not they're even a thing. So for this class and for my purposes, we're going to call 0 a natural number. So natural numbers are 0, 1, 2, 3, those things you can count on your fingers. Integers are the natural numbers plus all the negatives of the natural numbers. So -1, -2, -3, and 0, 1, 2, 3 are integers. This is like a big Venn diagram here, so everything inside is included. Rational numbers. So the rational numbers include everything that can be written as a fraction. So a half, -2/3, 2.25. Anything that has a repeating or terminating decimal is rational. It also includes all of your integers and all of your natural numbers. Real algebraic, we're not going to talk about. However, we will combine those with the transcendental numbers to talk about irrational numbers. So irrational numbers are those things that cannot be written as a fraction. Square roots of non-perfect squares, uh, pi, anything that involves those kinds of things that cannot be written as a fraction are irrational numbers. Down here are their symbols. So again, this is not for us. Instead, we use an I for irrational. So natural numbers are N, integers are Z, thank some German dude for that one. Rational numbers are Q, quotient. Irrational numbers are I, and real numbers are R. Now you write them very specifically. You don't write just a regular old R. You have a double-lined R for the real numbers. So let me move my face out the way. Again, irrational numbers are ones that can't be written as a fraction. Rational numbers you can write as a fraction. And here's some examples. Again, whole numbers are out of there. We're not dealing with whole numbers. Whole numbers just, if you learned about them in elementary school, they were natural numbers plus 0, but we're going to consider 0 a natural number. And it just depends on who you talk to as to whether or not it counts. Now, let's look at the systems here. So here's a chart. We're going to fill it out. So the whole thing is going to be our real numbers. And if we think about it, we have two things split. We have the irrational split with the rationals. Now we are going to have to get rid of one of these lines because, again, we don't do whole numbers. So for our purposes, 0 is a natural number. These are our natural numbers. And you should double it, but my rock is really thick and I have terrible handwriting. Something doubled like this, I guess. Yeah, I suck at that. Here's a nice picture of it right there. It should look like that. So we have our natural numbers, and then we have our integers, which again are a z. I'm gonna just write them like that. The only thing I'm gonna be picky about is the r for rationals. Make sure that's doubled, because that's easy to do. So naturals, integers, rationals, irrationals, real numbers. So the letters again, I'll write them over here. This doesn't exist. Irrationals, rationals, integers, and natural numbers. And we're going to go with 0, 1, 2, 3, etc. -1, -2, 0, 42, 3/5, -1.1, 2, irrational number square root of 2, pi, negative e squared, who knows, whatever. All that stuff, those are irrational numbers. That's just some examples. So let's talk a little bit more. We just talked about the real numbers, but there's actually more numbers. We also have the imaginary numbers. If we combine the real numbers and the imaginary numbers together, we get the complex plane. So if you think about your x and y coordinate plane, think about r's, the real numbers, as the x, the imaginary numbers as the y, and that entire plane creates the complex number system. So if we put together any of those two things, we get complex numbers. So imaginary numbers are represented by a cursive I, like this. So that's the imaginary unit. I is the square root of -1. Now we'll get more in detail on this much later. Well, depending on who you are. We'll get to this later, not today. But it's out there. Just know that it's there. Real quick, let's look at these. We're going to name all the sets that they belong to, and I'm just going to do very few of them. So it's a negative number, so that cuts out a natural number. But it still is an integer, and all integers are rational numbers, and all rationals are real numbers. That's a square root, but we have to simplify it first. Is square root of 30 nice? No, it's not, so this is irrational. But it's also a real number. Oh, here's a nice one. Negative, so that cuts out natural, square root of 81. Is square root of 81 nice? Yes, it is. This is the same as -9. You always have to think about something in its simplified form. So this is actually an integer, which means it's a rational number and also a real number. Down here, that's the same as 1. So that's everything. That's natural, a rational, oops, forgot integer, and a real. It's everything. So if you're not sure, this line, that means it's repeating. So if it's repeating, it is rational. This turns out to be a 0, so that's everything. Anything interesting? This is actually a nice fraction, so that's rational. Just got to think about things in their simplified forms. The other thing I want to talk about is properties. So the commutative property. A plus B is the same as B plus A. We can move things around. And that goes the same for multiplication. I'm going to use the asterisk for multiplication is equal to B times A. That's the commutative property. Associative property, that's going with grouping. Let me do this. A plus B plus C is equal to A plus B plus C. You can group them in any order you want. You could even do A plus C first. Doesn't matter. And same thing for multiplication. We just change these to multiplication symbols. It holds true. Yeah. The identity. So identity means you get whatever you started with back. So if we're adding something, A plus what is equal to A? A plus 0 is equal to A. For multiplying, though, A times what is A? A times 1 is A. So those are our identities. And the inverse is whatever you do to get your identity out of it. So A plus negative A gives us 0. That's the inverse property. A times what gives us 1? Because look, we're multiplying, so we're trying to get 1. 1 over A is going to give us 1. And we could do a few examples. I'm not going to do them all. But like 3 plus 2 is equal to 2 plus 3. That's what it would look like. 4 times 3 times 2 is the same as 4 times 3 times 2. So if we think about it, 4 times 3 is 12, times 2 is 24. 3 times 2 is 6, times 4 is 24. It's the same thing, either way we do it. Identity. So 3 times 1 is 3. Nothing interesting there. Inverse. 5 times 1/5 is 1. Now, we didn't talk about the distributive yet. Let's do that. So the distributive property does go both. I just froze my computer. Hang on. The distributive property does go both ways. Hopefully it unfreezes. There we go. So A times B plus C is equal to AB plus BC. Oops, sorry, AC. So A times B, A times C. We just distribute it to everybody in there. You'd be more familiar with it like this. If we distribute that 3, that's equal to 3x plus 2 times 3, or 3 times 2, which is 6, of course. That's our properties. Real quick, let's look at an example. It's equal to 0, that's the additive. Well, let's look. It equals 0, that's the additive inverse. On all of them but the distributive property, it's important to indicate whether you're adding or multiplying. So if you're doing both, that's right away distributive property. This is the multiplicative inverse because it's equal to 1. What do we do here? We changed our grouping. If we change grouping, that's associating, that's I can't spell, sorry. That's the associative property, there we go. Associative property of addition. I'll abbreviate. And let's do this one. That's the additive identity. There. It equals itself, that's an identity. We're adding, so it's the additive identity. Name the additive and multiplicative inverse for each number. Let's do 2 of these. To get -8 to be a 0, we need to add 8 to it. To make it equal 1, we need to multiply 1/8 and make it negative. 6w, we need to add a -6w and multiply by 1 over 6w. Easy peasy. So, I want to talk about this one. Additive, easy enough, -2/3. Multiplicative, flip it upside down. 1 over 2/3 is 3/2. Boom. So I think that's about it. Closure. So if you are closed, that means you get the same element, same type of element out. So if you're having natural numbers, they'd be closed under addition, because if you add 2 natural numbers together, you get another natural number out. If we multiply 2 integers, we get another integer out, so we're good. So -3 times -3 is 9, still an integer. Anything you do will still be closed. Irrational or closed under subtraction, false. Pi minus pi is 0, which is a natural number, which is not an irrational number. So that's a counterexample there. Whole numbers, that's called out as natural. Closed under division, that's definitely false. 1 over 2 is a half. So yeah, that's not. Odd or closed under addition, well, let's think about it. 3 plus 3 is 6. The closure. If you get the same type of number out, you're closed. If you don't, you're not closed. All right, that's it. Hopefully it wasn't too long of a video. I'll post the lesson material and the homework. Homework is what I expect you to actually do for the assignment. The lesson material will be this that we went over, including the examples I didn't go over if you want some extra practice. Goodbye.